Welcome to the day 2 of CMDB Expert series. So imagine an IT environment where nobody knows exactly what servers exist, what software is actually running, or who owns that. I mean, it's just pure chaos, right? Well, that's exactly what happens when you have an unmanaged IT setup without a structured, reliable foundation. Today, we are demystifying the CMDB, the configuration management database, and we are going to zero in specifically class design and baselines. We look at exactly how to take that operational chaos and turn it into a highly structured, reliable source of truth. Okay, let's dive right into this. Here's our step-by-step roadmap for today. We are kicking things off with the CI class hierarchy, then we will move into attribute inheritance. After that, we are going to cover baselines and system drift, look at the CI lifecycle, and finally wrap the whole thing up with managing schema governance. So starting off with section 1, the CI class hierarchy, or as I like to call it, building the blueprint, it's absolutely crucial to understand that every single CMDB organizes configuration items or CIs it into a very strict hierarchy. To really anchor this concept, let's start at the very top of the tree with the configuration item root. This is the absolute base layer of the CMDB taxonomy. Every single other class we are going to talk about today descends directly from this one point. Think of it as the foundational blueprint for the entire system. It holds those universal properties that apply to literally everything in your IT environment. Stuff like a name or an owner. Now, as we branch down from the root, the hierarchy splits into two distinct layers. First, we have abstract classes. Think of these strictly as templates. You never actually instantiate them directly or create a specific record for them. They exist purely to hold attributes that are shared by their children. Things like your general hardware or server category. Then contrasting that, we have concrete classes. These are the actual physical or virtual records you're creating in the database. They are the leaf nodes at the end of the branches, representing real world assets you can touch or log into, like a specific physical server or a virtual machine. Alright, let's do a quick knowledge check based on that blueprint. Imagine a class called server that's never directly instantiated, but it shares attributes with both a physical server and a virtual machine. So what is this example of? Well, if you guessed an abstract class, you completely nailed it. It's just an organizational template, not the actual server record itself. Moving right along to section 2, attribute inheritance explained, or as it's often thought of, family traits. Just like passing down genetic traits through a family tree, classes in a database pass down their attributes. Let's walk through how this inheritance cascade actually works. In step 1, the root CI establishes those universal attributes we talked about, like name and status. Then moving to step 2, the abstract hardware class inherits those traits from the root, but it adds its own specific trait vendor. By step 3, the abstract server class inherits name, status, and vendor and adds its own specifics like RAM and CPU. And finally, in step 4, the concrete physical server inherits absolutely everything from above and tracks on rack and power draw. This is super crucial. We want to keep this schema incredibly clean and dry, meaning don't repeat yourself by only adding new specific attributes at the exact step when they are actually needed. So let's test that logic out. Can you name one attribute that belongs on the physical server class but not on its parent server class and explain why? Think about a family tree analogy. The answer would be something like rack or uposition. And why is that? Because those physical space attributes only apply to physical hardware. They literally make no sense for the virtual machines that also share the exact same parent server class. By placing the attribute correctly, we don't force virtual machines to have empty, confusing rack fields. Now, what's really interesting about section 3 is how we shift from theory to reality. This is baseline and system drift establishing the gold standard. So we are moving from the nice, neat structural strategy of the database into the messy operational reality of actually keeping it accurate. To pull that off, we use something called a configuration baseline. A baseline is a formally approved point-in-time snapshot of a CI's attribute values. It is the definitive known good state. Think of it as the ultimate binding contract between your change management team and operations. Once this baseline is logged in, normal is officially defined, and any change has to go through a formal request process. Let's break down exactly why this contract matters so much. Using a real-world example, imagine a server named pod web01. If the baseline OS version for that server is Ubuntu 22.04 LTS and it changes unexpectedly, you've got an unauthorized OS change on your hands, which is a massive security and compliance risk. Or say the RAM suddenly jumps from 256 gigabytes without a corresponding change. Record operations just gained a major troubleshooting blind spot. And what if new open ports magically appear alongside the expected ones like 22 and 443? You've just exposed a potential new attack surface. Undocumented changes lead directly to major vulnerabilities and operational incidents. And that brings us to a very simple yet incredibly dangerous drift. Drift is simply when the current value does not equal the baseline value. Whenever a change happens outside the approved process, your system drifts. We really have to anchor ourselves to the reality that detecting this drift is absolutely critical for your stability and security. Unplanned changes are a leading cause of incidents strictly because nobody else on the team even knows they happened. Let's see if you're tracking with me here. Your database server pod DB01 shows an OS version of Ubuntu 20.04 out in the live environment, but the formally approved baseline says it should be 22.04 Ubuntu. What's this dangerous condition called? Well, if you said configuration drift, you're exactly right. Spotting that kind of discrepancy early is exactly what keeps your whole operation afloat. Moving into section 4 now, the CI lifecycle or catching the drift. So CIs aren't just static objects sitting in a database. They live, they breathe, and eventually they retire. We have to meticulously track that entire journey, and this brilliantly illustrates the rigid lifecycle of a CI. One day one server is ordered, by day 5 maybe it's in stock, skip to month 1 it's in use, a few years down the line, say year 3 it goes in maintenance, by year 5 it's retired, and year 6 it's fully disposed. The absolute crucial point here is that status transitions should only ever happen through approved processes. I mean, a server sitting in a retired status should never ever be empowering a live business service. If it is, your data is completely misleading your teams. So how on earth do we track all this without making ourselves totally crazy? Well, the golden rule of CMDB population is this. Mature implementations aim for about 80% auto-discovered data versus 20% manual entry data. You absolutely must automate your infrastructure discovery with scanning tools because manually maintained data goes stale incredibly fast. Honestly, humans forget to update spreadsheets, auto-discovery tools don't. But wait, if automation is so amazing, why don't we just automate it 100% of it? Why are auto-discovery tools well suited to infrastructure CIs but poorly suited to things like business services or vendor contracts? Well, think about how a scanner actually works. Discovery tools scan networks and APIs. Business services and contracts, on the other hand, are abstract organizational constructs. There is no IP address for an SLA tier, and you obviously can't run a port scan on a piece of paper. So those 20% exceptions still heavily rely on manual entry. This brings us to our final section, section 5, managing schema governance, which is really all about keeping order. We have built an incredible, highly logical blueprint today, but without strict governance from a dedicated configuration manager, this entire database will inevitably collapse. Let's look to how quickly things can go wrong. Imagine a bad approach to schema updates. Your team wants to say cloud region and track it. If you just slap the entire attribute directly onto the root CI, you've just polluted every single CI type in the entire database. Suddenly your physical keyboards and software licenses have this empty, confusing cloud region field. The much better correct approach is creating a specific cloud VM subclass under the virtual machine class. You've got to keep the attribute precisely where it belongs, which brings us to a frankly critical rule of thumb for any CMDB owner. Never add an attribute. You don't have a process to populate. I really want you to internalize that an attribute that nobody actively updates is actually far worse than having no attribute there at all. Why? Because it actively misleads the operations teams who are trusting the CMDB to make really high stakes decisions. So I want to leave you with a final slightly proactive question to chew on. How much stale data is currently rotting in your organization's database right now? Like how many attributes are just sitting there without being updated? How much stale data is currently rotting in multiple parts of the CMDB? And that wraps us our explainer on class design and baselines.